these two charges, right? And they're isolated. So we've got the negative charge and the positive charge. And then if we were to draw our electric field in here, remember it's going to go out of the positive charge and into the negative charge. So what that's going to do is make these longer field lines curl in like this to form continuous lines in like that. And we're looking at what's the magnitude direction of electric field at point midway between these two. So right here. So it's going to have a contribution from the positive charge and a contribution from the negative charge, and they're going to be in the same direction vectorially, so their magnitudes are going to add together. Right? Does that make sense? Okay. Since it's halfway, each of these is going to be 0.055 meters over 2 away, and you would use that E equals 1 over 4 pi epsilon naught Q over R squared. And you would say, well, the electric field due to the positive is going to be added to the electric field due to the negative, give the electric field total. And you can algebraically add up the magnitudes because the vectors are linear at that point. So really it's a substitution game there. Be careful of your negatives and positives are only to help you establish the directionality. When you put them into Q, you don't need to include those. Other trick with this one would be realizing that, say, 1 over 4 pi epsilon naught has a value of 8.988 times 10 to the 9th. So you can store that value in your calculator and just use it. All right? No, the value of the Q for the negative charge would be 8, for me, is 8 microcoulombs. So 8 times 10 to the minus 6 coulombs, and for the positive 4 microcoulombs. .988 times 10 to the 9th. Yep, that's what I'm meaning down here by the E positive plus the E negative. So vectorially they add together, and since they're in the same direction, we can also say, okay, well, their magnitudes would just add together also to be the final E field. Oops, go back. To be the magnitude of the E field. So you should have that the, towards the negative charge should have been my choice. How do you store? You put in the, I'd show you on my calculator, but since they changed middle school servers, mine doesn't work. But you put in the number, you use the arrow key. Number goes first, and then the STO with the little arrowhead down the bottom. Yeah. So 8.988 E to the 9th, store, and we'll make that K up. Yep. You want to use mine? This is stored in minus K. Point charge of mass 1 gram at the end of an insulating cord of length 50 centimeters. Field, the pendulum position is shown in the figure, the charges, H where the lowest vertical position in the field points to the right. The figure determines the magnitude and sign of the point charge. Ah, it's in equilibrium, which means all the forces have to balance on it. So if I was to do a little free body diagram here of my charge, there would be a tension up this way, the weight of it down this way, which means there must be a force from the electrical field that way to balance out those other two forces. And what type of charge feels a force in the direction of the field? Positive or negative? Positive, yay. So, yay. So, then I can do a little geometry. Oh, geometry. Where this is 50. Since this is 15, this side is 35, right? So theta here is inverse or arc cosine of 35 over 50, right? It says h equals 15 above the lowest vertical position. See the h on the little diagram? So that's the height above the lowest position here. So it's swung up, and now vertically is 15 centimeters higher, which means if I make this right triangle like I did, the hypotenuse is 50, and that whole line there on the vertical would have to be 50. 15 of it's outside the triangle, so that the adjacent side to the angle is 35. For what? It's all good. So now, since this is in equilibrium, I can also do this as a vector diagram, form another nice right triangle where this is force E, and this is F sub G, and this is also theta. Since the tension has to be in the cord, and I know the gravitational force is directly downwards, so I can say that tan of theta equals Fe over Fg, right? I'm interested in the charge, so I'm going to rearrange this so I have Fg is tan theta equals Fe, which equals, remember, electric field strength is F over Q. So the force is E, the electric field strength, times our charge Q. Do they give us the electric field strength? Yeah. So now I've got the mass, so I can do mg tan of this really ugly arc cosine of 35 over 50. You might evaluate that ahead of time if that scares you. All over the electric field strength E equals Q. Of course, you're going to be careful. Make sure you put your mass in kilograms and your electric field strength be that. So let me try mine while you try yours. We'll see. So 1 gram. 15,000 newtons per kilo. I did a little geometry back up here, and they told me that mine vertically was 15 centimeters above the lowest point it could be at. So think of it like a pendulum. So when the string is 50 centimeters long, so that's the geometry. Well, you got centimeters over centimeters, so you can just leave them.